Yeah, and I also asked that question because I think it's also a question of time, right? If you would obviously do this intervention, in humans, the lifespan of a human is, what is it, the average right now? 80, 75, 85, whatever. So it'll take you much longer to actually see some of the effects than in other organisms like
So
mice.
that's very true, but it's less true than you might think because we're doing damage repair. So in these experiments, we start when the mice are already within 1 year of their average longevity. So we get results in a year. We can see whether the mice are living longer. Whereas if we were doing things that had to start early, it would take 2 or 2.5 years. Similarly in humans, except in humans, the difference is much bigger. Supposing we want to get 20 years of additional life in humans, and we start an experiment in humans that are 60 years old. Okay, so they've got 20 years to live or so on average, right? And we want to make it 40. We want to get those people out to 100 on average. We would not have to wait, 40 years or even 25 years to see whether we were having an effect. We could see the effect in the first few years because we know what biological rejuvenation means in terms of mortality. We could look at simply what proportion of our treated people are dying. And a 20-year postponement of aging, 20-year rejuvenation, would equate to roughly a factor of 6 reduction in the likelihood of death, in the frequency of death. So that's a big number. You don't even need to do a big trial, right? So you can take 100 people, and when they're 60, you'd expect maybe 10 of them to die in the next 5 years, something like that, some small number like that. Okay, and if your treated people, only 2 of them die in the next 5 years, then you've got a statistically significant result already, even with only 100 people. Right? So this is not actually as hard as it sounds, so long as your effect size really is that big. Now, of course, there are other ways that people are trying to develop to measure biological age in a useful manner. And there is lots of progress on this, and there's lots of money around it now. There's particular interest in something called epigenetic clocks, which are measures of biological age that started being developed maybe a decade ago. And they're pretty good now. They can make reasonable predictions of how long it's going to be before you get sick. At least they can do so in mice, and they can pretty much do so in humans. The difficulty with these things, the shortcoming that they currently have, and that I think they're going to have for a while yet, is that they need to be robust across interventions. In other words, you need to be able to use them as a surrogate endpoint to say, okay, this really does predict whether the intervention has worked. And at this point, we can't say that. Of course, the difficulty is that you create your epigenetic clock or whatever by looking at existing data. And by definition, existing data consists of people who have not had therapies that have not yet been developed. Right? So you don't know whether the clock's going to work on therapies that you try it on later on. We shall see. But certainly mortality is a damn good assay. And if you're talking about mortality of people who are not yet sick, people who are in their late middle age, like 60 or 70, then you're talking about genuine reduction of biological age as opposed to treatment of a disease.
How could I, measure this today? And is it so, as a human, my biological age, but also maybe the effect of some rejuvenation? And, is it just the one biological age, or is it that different parts of my body actually have a different age?
So first of all, absolutely, there's not. One can try and come up with a single number, but for sure, different organs and tissues will have different things going on in them that will translate into different biological ages, and you're only as old as as young as your weakest link, right? So that's certainly an important thing to take into account. But to answer the essence of your question, what can you do today? The thing is, we don't need these sophisticated omic technologies to assess biological age, at least reasonably well. We can assess it based on function, on things like how fast can you walk, how tightly can you grip something, how good is your memory, things like that. And these assays have been developed over many years, also for mice, incidentally, and we've been doing those assays. But yeah, I mean, so they are still probably the best measures of biological age. Of course, one can also do metabolic analysis. One can take blood samples and measure, hundreds of things in one's blood that typically change with age and get some kind of correlation, some kind of indication of how biologically old one is by each of those measures. And then one can, create some kind of weighted average.
You said grip strength. How is grip strength a factor for biological age?
Yeah, it's interesting, isn't it? But it is. It's not so much a factor as an indicator, a readout.
Mhm.
Muscle is a really important part of the body. Muscle quality, as well as muscle mass. It's not just in terms of how strong you are. Muscle is a reservoir. We've got so much of it that it is used to buffer, to stabilize things in the whole body. So the most significant one, of course, is sugar. The way that insulin works, everyone knows about insulin, right, is that it stimulates muscle to take sugar out of the bloodstream and store it in a metabolically safe way, so to speak. And this is useful because it means that the sugar is not floating around in the bloodstream doing damage, like reacting with proteins and things. If you've got less muscle, then you've got less ability to buffer, high sugar dietary intake, for example. And that's just one example. So yeah, muscle matters a lot. And the more you have and the quality it is, which is measured by strength, the better. And grip strength is just the easiest way to measure that.
Interesting. So if you look at the technology in the next couple of years, I mean, we're not predicting anything here for sure. But according to your research, what scientific and also what technological unlocks are needed to, realize damage repair, aging reversal at scale?
Well, first of all, let me talk about predictions. So I believe that if there's one single biggest error of judgment and mistake that the overwhelming majority of my colleagues in the biology of aging make and have made since forever, it is to refuse to make predictions about what's going to happen in the future in relation to intervening in aging. I've been saying this for 20 years, and it hasn't really worked. But I believe that we've got a huge problem there. Of course, this is pioneering technology, and therefore, any prediction that one makes has to be probabilistic. So when I say that I think we will reach longevity escape velocity in 12 to 15 years, I am always very careful to say that I believe we have a 50-50 chance of getting there within 12 to 15 years, and that we have at least a 5% chance of not getting there for 100 years, right? Because we just don't know what unforeseen obstacles we may encounter. But overwhelmingly, my colleagues refuse to say things like that. And I believe that that's a huge problem because the absence of expert predictions leaves non-experts in a position of having to, figure out their own predictions about what's going to happen. And of course, since we have made pretty much no progress against aging in the whole of the history of civilization, despite all manner of people over the years saying we could, the inclination is to assume that we never will. And therefore, that slows down research because it means that if it's a mug's game, it's a pipe dream, then one isn't going to be very interested in having one's tax dollars spent on it, for example. And so I believe that my colleagues have been massively shooting themselves in the foot all these years. It's gradually changing now. But that's what I wanted to move on to in answering your question, because the question is, how will it move on decisively? How will it change decisively? How will my colleagues start saying the things that I've been saying for so long? And I believe that that's the main value of the studies that we're doing at LEV Foundation. I believe that once we do achieve this 12-month postponement of the health decline of normal mice, starting in middle age, then all my colleagues will feel able, they will feel they have permission to say publicly things that at the moment they would not say because they would be scared of being accused of saying something irresponsible, right? And that's what's going to change everything. That's when, you know, influencers, you know, Oprah Winfrey, Joe Rogan, Mr. Beast are going to be out there, you know, saying, well, look, if we can do this, then we kind of have a moral obligation to do it as quickly as we can, to, you know, to alleviate suffering and save lives and all that. And the following day, it will be impossible to get elected unless you have a manifesto commitment to have a proper war on aging, you know, to take this seriously. And, you know, at the end of the day, elected representatives have one goal in life, which is to get re-elected. So, you know, that in a very real sense, that on that day, my job will be done.
It can't be unspoken. If it is out there, you can't take it back. I agree.